Let's consider the following problem. A small test charge plus q and a mass m is constrained to move along a line connecting two charges plus q d away on opposite sides. Find the period of small oscillations. Alright, so this does integrate a few things that we've learned so far, which includes basically the force and charge in one dimension, as well as basically what you must have learned in mechanics already, which is basically simple harmonic motion. Right? Let's begin by drawing a simple picture. So a small charge plus q, right, is constrained to move along a line connecting two larger charges on opposite sides. This is plus capital Q and plus capital Q again. And this distance here is d, and this distance here is d again. Right? Now, intuitively, you probably imagine that in this situation, because all the charges are alike, and this little charge Q is basically between these two charges, that the electrical force on this one will be exactly zero, and you'll be correct, right? But you can show that, and by showing that, it will give you an idea of basically how to do the rest of the problem. So let's consider the forces on basically on Q by, we'll call this basically 0, 1, and 2. So the force on 0 is going to be K Q1 Q0 over basically R10 squared R10 hat. Okay, now this in balance of coordinate system, this will be X, right? So this will be X hat because I'm going from basically 1 to 0, this direction here. So this will be K capital Q little q over the distance d squared x hat. Perfect. Okay. Now let's consider the forces, basically F2 on 0. That's going to be K Q2 Q0 over R20 squared R20 hat. Now R20 is this vector right here. Okay. R10. Let's label that vector. And what you'll notice, it points in the opposite direction as x hat. So this one will be minus x hat. So this will simply be K capital Q little q over d squared minus x hat. Right? So when we sum up the forces, F is just F10 plus F20. This is just simply going to be adding this together. This is a positive, this is negative, this would be 0 exactly. Alright, so when we talk about consider pure small oscillations, what we're going to consider is that if we move this object ever so slightly in this direction, right, such as at a new position right here, and we'll call this position X, alright, because of this is X. And we're going to consider X is much smaller than D, right? So, but we need to get this thing exactly, right? So let's write this thing exactly down correctly. So F1 on the position X now, this is just simply going to be K Q1 Q0 over R1 to X squared R1 X hat. All right. Now this stays the same. It's still in the same direction. So this would be again X hat, right? But this is a little different. This goes from basically d to d plus x. So it's d plus x squared, right? So if we put this together, this would be k q over d plus x squared in the x hat direction. Okay. Now we do this for f2x, right? This will be this. Everything looks almost the same. K Q2 Q0 over R2 to X squared R2 to X hat. This stays the same as before. This is just again minus X hat, right? Still pointing in the exact direction. We're just going a little bit distance shorter. But this vector, right, this little distance right here goes from basically D to D minus X now squared, right? So if we put this together, K q over d minus x squared in the minus x hat direction. All right. Now, if you look at these two things now, f1x and f2x, they are not exactly equal and opposite. All right. This is d plus x. This is a d minus x. All right. So how do we solve this problem? The way we solve this problem is to use this key fact here. All right. All right. And we've used this key fact here. What you can do is you can basically Taylor expand this one out. All right. So let's do a Taylor expansion. Okay. So the key Taylor expansion that we need to know is 1 over d plus x squared is going to be equal to 1 over d squared plus 2x over d cubed. Okay, important fact to know. All right, let me make sure I get the signs right, and the signs are in fact not correct. Minus sign. Okay. All right. So we're going to use this plus order x squared. Okay. So higher order terms will be x squared. Okay. But because d is much less than x is much less than d, this is the lowest, what's called the lowest non-trivial term that we need to worry about. Okay. So let's do this now. So F, the force, which is the net force now, which is going to be equal to ma vector, well, ma because it's one dimension, which is m double x prime. This is going to be equal to f12 plus f1x plus f2x, right? So f1x plus f2x, these are vectors again. So this is going to be equal to, let's do this very carefully, k q q, right? In the x hat direction, I'm going to rewrite this as x hat 1 over d plus x squared minus now f2x 1 over d minus x squared. Now this minus sign got absorbed here, right? Everything else stays the same. There's the x hat out in front of everything. Okay. All right. Okay. Now if I want to do this right as a vector, I could rewrite this as an x hat, just to make things a little clearer. Okay, so now we're going to use our little Taylor expansion trick right here. Plug that in, right? K, capital Q, Q. All right, we'll drop the x hats for now. All right, this becomes 1 over d squared minus 2x over d cubed minus this one is a 1 over d squared, okay? And this one I'm going to replace a minus with the minus with the minus, which would be, I believe, it's going to be, if I do this correctly, this minus will come out. Again, that minus will be, so it'll be a minus, a minus, a minus. So it's your overall minus sign. Minus 2x over d cubed. Okay. And plus higher order terms, right? Which I'm going to drop now. Now let's look at this very carefully. Plus 1 over d squared minus 1 over d squared. These cancel out. This is the fact that like you're very close to center, so they nearly cancel each other out. And these are the correction terms here, right? So this is going to be equal to m x double dot, which is ma, is equal to k q q. Okay, let's bring out the d cube here. Bring out the 4 to a minus 4. Bring out the minus sign x. Now, if I divide by m here, that becomes a 1. And now I'm going to recall the simple harmonic oscillator, which is x double dot is equal to omega squared x, or minus omega squared x. All right? And if I look at this thing, and I look at this thing, this term right here plays the role of omega squared. Okay, right? And so we know the solution for this one is basically x is equal to a cosine of omega t plus delta, right? We know that's the solution, right? And the period is just 2 pi over omega, right? So the period of small oscillations in this case is just you just replace this omega here with this effective omega. So t is equal to 2 pi over omega, which is going to be equal to this omega squared, remember, 2 pi over the square root of 4k q over md cubed. All right. Now, if you want to get fancy, you could basically kill the 2's off. Be pi, and then we're going to write this as mdq over k q little q. And then we are done. Okay, hope that was helpful.